Okay, let's talk about the deformation of rocks. We will look at the triggers or a few triggers to the creation of faults and folds. First of all, a rock is said to be deformed if it's been either broken or bent due to the stretching or squeezing or the vibration or the shaking of the earth crust in that area. There are a few triggers: plate movements in the form of extensional, translational, or contractional plate movements. Basin loading, where you have withdrawal or preferential movement of the underlying substrates in certain directions, in certain manners. They will also impact the amount or the kind of deformation you have on the overlying rocks. Space constraints, and this speaks to the difference in the rate at which deposits find their way into a basin versus the rate at which accommodation space or subsidence actually occurs in that basin. So the interplay of these rates actually determine sometimes the kind of deformation you have on the overlying or the resident rock mass. Stress release is another factor, especially in unstable terrains or where the rocks are actually in critical conditions. They either snap or faulted. They are faulted, or sometimes they are folded. And then some rocks are actually preferentially deformed along a dominant or a dominant plane of weakness. So we'll look at some of these examples. Deformation from plate movement. Now, plates the earth plates may move away toward or side by side each other. When they are moving away, like we have in this first case, we say it's extensional plate movement. In the second scenario, where you have two plates moving towards each other, in this case, supposing you have the continental crust on the left riding on top of the oceanic crust on the right, when that happens, you have certain kind of deformation of the rocks in this area here, like we see the creation of some big mountains or structures. In the third scenario, you have the plates moving side by side each other. Sometimes may be accompanied by some amount of coming together or moving away from each other. We'll look at that. So these are typical or example of the rock behaviors or deformation that you have in these different terrains. In the first scenario, where the plates are moving away from each other, typically what is happening is that the crust is actually being stretched, and the stretching of the crust in opposite direction kind of creates a space. So what you now have is the normal faulting or the collapse of different blocks of rocks because of creation of space in the middle. In the second scenario, you have two plates coming to each other, so there's shortening of the crust, and when that happens, there's a lot. First of all, there's a lot of heat or heating or melting that happens at the interface, where the plate on the right, which is in this, let's say, the continental crust, right on top of the oceanic crust on the left. So in that interface, there's a lot of heat produced, and that creates a bunch of eruptions in form of volcanoes and all that. So that's one. And then secondly, the rocks in this area are also, for the most case, folded. Creates a huge mountain. They are folded. They are deformed. Okay, and they are also usually they get in the plastic mode because of the heating and the melting. Because of course the temperature is very high for the rocks. So what we see is the creation of bumps, unlike what we had in the first case, where you have creation of grabons and normal faulting. In this very case, you have dominance of bumps, anticlines, and folded and deformed and melted rock units. In the third scenario, where the rocks move side by side, it could be we have side by side movement in the first place is called translational movement. However, we may have some degree of moving past each other, but at the same time coming together, and that's called transpression. When that happens, we have this kind of behavior where you have more of what we call pop-up structures at the shallow end. So the two blocks, in other words, both blocks are moving past each other, but they're also coming together at the same time, so it creates a pop-up. In the other scenario, the both blocks or both plates rather are sliding past each other, but Again, at the same time, they're moving further away from each other. And when that happens, it creates what is called a pull apart basin. You will notice for both cases that the faults in the translational system, they are usually subvertical, and that's one thing that kind of distinguishes them from where you have extensional signature. So in this case, the faults, because the movements are lateral, the faults are usually vertical to subvertical. Now, this is another case where you have deformation of, in this case, I'm going to focus on, let's call this layer 1 and this is layer 2. So we're focusing on the deformation of layer 2, right? So this is the case where the deformation of the overlying rock units 2 is actually impacted by the behavior of the underlying substrates. Now, in this very example, let's consider that at time t1 in this area, we actually had two layers deposited, the substrate and the overlying rock mass. So at this early time, you don't have active loading, or you can say you have loading, but at a very slow and consistent rates. So when that happens, the overlying mass of rock actually takes the sub-horizontal geometry that we see. So generally, the kind of whatever deformation, whatever loading we're seeing here is actually driven by gravity. Now imagine that at time t2 we have more a new episode of loading, and quite at a much rapid rate also. So what you now have is these layers that we had 1, 2 are now become 1, 2, and 3. So, but what that when because of the rapid addition of weights in this part of the basin, the underlying incompetent substrate moves further basinwards. However, in this case, we're assuming that there's some kind of barrier that prevents it from moving as it prefers or as it wants. So when that happens, what you now observe is that it creates some kind of buckle, and that's actually because of course the law of conservation of mass. So either way, this mass of rock will have to go somewhere. If it can't go lateral, it's going to go vertical, and when that happens, it creates a bump. And what that means is that the overlying layer 2 will actually take the shape of what the underlying substrate has created. So this is a case of deformation driven by the behavior of the underlying or the basal substrate. So this is another case where we have deformation due to space constraints. So this is just an easy example. So let's consider that at time t1 in this area, we had slow rate of basin loading. So deposits are prograding in basinal, of course, in the basinal direction. At this early stage, what you have is dominance of normal faults and some early, very low angle thrust in the distal areas. Okay, so at time t2, with continued loading or rapid deposition of sediments in the basin, what happens is that the underlying substrate moves further basinwards rapidly, and there's a lot that happens. You have the creation of detachment folds, more like symmetrical folds. You also have lots of diapers, and then one other important thing is that you have the creation of fault thrusts or truss faults, and in some cases you could call this reverse faults for the very high angle candidates. And now the key thing is that these faults are actually called fault thrusts because of the direction in which they are dipping. At this second stage, the deformation we see is actually influenced by the difference in the rates, the rate at which the basin is being loaded with deposits versus the rate at which accommodation space is being created by the subsidence that happens, right? So if this behavior continues up to time t3, now there's something that now happens different from what we saw at time t2. What was originally, at time t2 we had this fault thrust and we had this gentle back thrust fault that is developing, but at time t3 we see that the back thrust has become the dominant fault, while the pre-existing fault thrust is now the minor one. And that is because this whole package that is moving in this direction at time t2, because of the difference in the rates, at a point there is what is called what we call space constraint, and that actually triggers like a backstepping of the whole rock mass, and that kind of triggers the creation or the development of this fault in the opposite direction. And that's kind of in opposite to the direction of deposit inflow from in this area. So what we're saying is that the behavior, the earlier the earlier fault that we see, which dips in the basinal direction in the form of a fault thrust, with prolonged and increased rate of basin loading, at a point the whole of this distal area becomes saturated. There is now too much sediment than the space can occupy, and when that happens, there is going to be some form of back pushing. So the whole of sediment here, the whole of the package here, is actually pushing back because it doesn't have enough space to go further down the basin. So when that happens, it creates some kind of back push or pushback, and that actually triggers the creation of this back thrust. So what this is saying is, whether we have forward thrust or back thrust, it is all in reaction to the rate at which the deposits are coming to the basin vessels, the rate at which space is actually being created for those deposits to occur. Now, one other key message here is this. In this area, the example we're citing here is actually from a passive margin setting. There are other basins where what actually creates movement in the opposite direction is actually as a result of a plate movement or some active deformation in the basin. But in this very case, it's actually totally driven by gravity sedimentation or gravity settling of the deposits, and the back thrust we see is purely a result of space issues. So overall, one other final thing we need to note is the geometry of the basal rock is key. Because some of the early bumps you see, for example, if I highlight this at time t1, the early bumps you see is actually driven or sometimes triggered by a gentle elevation of the underlying basement rock. So in this area you have a bump, and that's actually triggered by the gentle increase in the elevation of the basement. And as things progress, the rates of deposition versus the rate of subsidence, the interplay of both rates actually now come into play, and that determines what kind of deformation we're going to get, if it's going to be a forward thrust or a back thrust, or if things are going to create an anticline in the form of a buckle or not. So there are some other cases where deformation might be as a result of stress release. This is a case where you had a pre-existing surface that is stable, sub-horizontal, but maybe at a point it's some zone of weakness and it becomes unstable, and then it takes this geometry. Now what happens after some time is that the weights you have here, the amount, because of this difference in this elevation, there's some instability. So there's a pressure on this hinge, and with time that could develop into it originally starts as a joint or a crack, but with time, with more load on top of this part of this on the eastern part of the rock, this whole mass eventually sinks, and that could lead to the creation of a normal fault, which we could actually see. So this is a case of something that was originally sub-horizontal but a little bit inclined, and also sometimes because you had a zone of weakness or a zone along which you had some degree of fault in fracture or some joints, that zone could develop and become a zone of weakness, and with the bending of this rock it becomes unstable, and in this very case you have more load coming in here on the eastern part, and that means in no time there's going to be some breakage of this whole layer of rock that was originally continuous and unfaulted. In some other case, you could have fracturing or faulting at the crestal part of a fold. Now, this is a case of if this fold was of low amplitude like this, we wouldn't have this. But because it's gone from a low amplitude fold and maybe by some configuration it became more tightly folded, and it creates this much tighter crested anticline. So at the crest in this area there's going to be some kind of stretch or some kind of excess stretching of the rock matter here, and that creates some little fractures which eventually sometimes might develop into a full-blown faulting, and you could actually have a normal faulting at this crestal parts, and that's really as a result of the stretching of the rock beyond its limit. And this is more where you have mostly clastics, not rock that take plastic shape. If the rock is more of a clastic and has a tendency to break or brittle, then that's where you have behaviors like this, where you have keystone faults or crestal faults form at the top of the anticline. So that's all we've got to share for now. Thank you for listening. Do not hesitate to let us know if you have questions. Follow us on YouTube, on Facebook, and send us an email if you have a question. Let's start off the discussion on this.